Alright, so we looked at multi-core programming briefly already. We saw that core represents processor or CPU. So when I say multi-core, it means there are multiple processors or multiple CPUs available within the same system, and each of them is going to be working on one process or one thread. So multiple threads are getting executed parallelly. So your output is increased or your efficiency is increased. That's the whole idea of multi-core programming. But that is not as easy as it sounds, because there are some challenges which come with this multitasking thing. So you have to first identify tasks which are independent and can be run concurrently. So what is the problem here? More often than not, in your computers and your processes, there is a dependency. There is something like a prerequisite, co-requisite sort of a situation where you cannot start process P2 until and unless P1 has been finished. So if there is that kind of a situation, you cannot make P1 and P2 run parallelly on two different CPUs, although you have two different CPUs. So you have to identify tasks and subtasks, or processes and threads, and you have to make that division of processes into threads in such a way that you can run as many threads as possible in parallel at the same time. So that identification and splitting is one challenge. The second is load balance across cores. So if you have 4 CPUs, you have to make sure all 4 of them are occupied as much as possible, at least. It does not make sense to leave one core idle all the time and to put all your load on the other 3 cores. So this might sound like a very obvious thing intuitively, like if you have 4 CPUs, why would you not use all 4? But the catch is, let's say the first core is working on thread T1 corresponding to a process P, and you have a second core. Now if you have another thread T2 also corresponding to the same process P, if you are going to wait for the first core to finish T1 and then you ask the same core to work on T2, then there is no context switch, because it's the same process, same processor, just a different thread. So there is no context switch. Whereas if you take the second thread and give it to another CPU, there has to be some context switch, some overhead, some time being wasted. So the point I am trying to convey is there is a trade-off. So when you are using one CPU to execute all the threads corresponding to one process, it will take time, obviously, because it can only execute one thread at a time. So if you have 10 threads, it will take 10 units of time, but context switching time will be eliminated. Whereas if you use 4 different processors to work on 4 different threads corresponding to the same process, then in terms of output, obviously instead of 1 thread per unit time, you are producing 4 executed threads per unit time. So in that sense, you are speeding things up, but that context switch, that taking the context of the TCP, updating the contents, that extra time you are going to incur. So you have to balance the split of tasks or balance the mapping of threads to cores in such a way that an optimal balance in terms of this time trade-off is attained. So that's what I mean by load balance across cores. Next up, we have data splitting. Again, when 2 or more threads are dealing with the same data and when they are going to be working with different processors, both processors might be competing to access the same locations. So that dependency is there. Data splitting, in the sense, is it possible to split the data into 2 subsections or subunits and give one chunk of data to the first core and another chunk of data to the second core? That might not always be possible. It depends on the context, the nature of the task, nature of the process. But yeah, that is a challenge when there is a dependency in terms of data. So 4th point is data dependency and synchronization. So the idea is multiple processors, multiple threads competing to access the same location. There is a sort of clash. How that clash is avoided, or if it happens, how it is handled, is what the 3rd and 4th points deal with. And then of course testing and debugging. There are issues which come up with testing and debugging. We are not going to go into all of these challenges in detail and learn about how to solve them and all. Just trying to convey the point that multitasking or multiprogramming is not as simple as it seems, or it is not completely all benefits without its own share of challenges. So here, on that note, we'll also take a look at two terms which are very relevant in this context: data parallelism and task parallelism. So parallelism, first of all, means you're doing things in parallel or concurrently, which is what the whole idea of multi-core programming is about. So data parallelism is about distributing subsets of the same data across multiple cores and performing the operation on each core. So the analogy I like to give for this is your merge sort algorithm. So for those of you who are familiar with merge sort, well and good. Just in case you want me to brush up on it, it is an algorithm to sort an array of numbers. So you recursively divide the array into half at every step, and you sort the halves separately and then you merge them back. So data parallelism in one sense is like that. So the data given to you in this example is the whole array. You're dividing it into two subsets, half arrays, and you're performing the same operation on each subset individually. Then you're combining it. So different subsets of an array are handed to different cores for sorting. So that's the idea of data parallelism. When you have a large chunk of data, you want to do something with it. You divide the data into different subsets, non-overlapping subsets. You give one subset to each processor and you ask all processors to do the same task. So you have 4 CPUs. You divide your array into 4 subarrays. You give one subarray to each CPU and you ask each CPU to sort that subarray. Then you take all the 4 sorted subarrays and you use some logic and you combine it. That is an idea of data parallelism. Task parallelism, on the other hand, means you are giving a different task itself to each core or each processor. So in data parallelism, each processor is getting different data but is doing the same task. In task parallelism, every processor is given a separate task. So for example, one thread is finding the minimum of an array, another thread is finding the average of the same array or different array. So why are we talking about data parallelism, task parallelism here is there are different ways in which multi-core programming can be accomplished. It is either you divide the same task into smaller subsets, you take the same task and you ask the processors to work on it with smaller chunks of data, or you take totally different tasks and give one task to each processor. The former being data parallelism, the latter being task parallelism. So those are two ways in which multi-core programming can be implemented depending on the context, depending on your data, depending on what task needs to be performed.